So a little bit about the CLS. I'm going to talk about one beamline. You got to keep in mind that there are many beamlines there. Beamlines are things where we bring light out of the synchrotron down to a specific research environment for particular problems. So I'm going to talk about one of them. Just keep in mind that there are many there, and all of them can be used in some sense for medical applications, but I'm going to talk about one that really has a very strong biomedical emphasis, and that's what's called Biomedical Imaging and Therapy Beamline, or BEAMIT. I love the acronym because it just works so well. We beam things. And that's kind of the purple thing up in the corner there. If you go by the north side of the CLS, there's this bump on the north side, and they're building a new beamline outboard of us called Brockhouse, but the one I'm going to talk about is this complex in the corner. So it was mentioned that I was attracted here. And I came here from Chicago, so there's a Chicago legacy there. But I'm a prairie boy. I'm from Oklahoma. But nonetheless, I came here from Chicago, and really what brought me here was what is here. This is an amazing place. There's a synchrotron on a university campus. That's unusual to begin with. We have the Western College of Veterinary Medicine. We have the RUH Hospital. We have kinesiology. We have the cancer clinic. We have all of these biomedical things in one place. And if you're from here, this may or may not seem unusual, but this is an incredible coalescence of biomedical things. And so if you think of a place where you want to do biomedical research, this is it. It's still small enough. We all know each other. I think it's an incredible opportunity for biomedical research. And I credit Sylvia and her colleagues for, in some sense, helping lead to that. This merging of basic sciences with medicine and other entities is, I think, a very powerful thing, and in some sense was partly started here. And of course, this is the beamline I'm talking about. I'm not plugging CTV in the corner there, but nonetheless, this is just a picture of the facility. So this is what we call a beamline. What we have are actually two beamlines. We have one that's sourced by something we call a bend magnet, fairly tame source of light or X-rays. And then we have another beamline that's called the insertion device beamline, and that one is the one that goes full length of the facility. And it really gives us access to X-ray energies that span the whole diagnostic imaging regime. So at the end of this thing, there's a big, what we call a hutch. And in that hutch, part of our mandate is to image pretty big things. And so there's a big thing standing on a big thing. That's me. And so this is part of our facility. Part of our mandate is to image something as big as a horse. And you might think we're crazy, maybe we are, but captured in this picture, other than me standing on this big thing, you see the big blue thing. Maybe it should have been green. It's a little bit green. But this thing will hold humans. So this is our human positioning system. You saw how PET-CT is done. There's a ring of detectors around you. CT, when you go into the clinic, there's a X-ray source and detectors that fly around you. Well, at the synchrotron, you're not going to move the source anywhere. So we have to spin things. We have to orient things. And that thing I'm standing by is part of that. And it's for a form of therapy. I won't be able to talk about that. But I just wanted to point out this rather large positioning system. And that's it down. And that's it up. So it's a pretty amazing gizmo. And I'd like to point it out, but part of our mandate is large things, but it's remarkable that we can look at little itty-bitty things. So this is a piece of bone. It's probably no more than 2 millimeters on a side, and you're looking at the cells inside that bone. This is work done by David Cooper, a colleague of mine in the College of Medicine. And in every one of these, I mentioned a trainee. Part of what we do is not just do research, but we're training a new generation of people. So all of these will be trainees in what's called the THRUST program here, which is a training program that merges synchrotron people like me with the medical community. Again, what I would view as part of the legacy of Sylvia. This is looking at stroke. So again, this is a stroke that's been induced in a rat. And you can see the big blobs there. That's the blood that's been collected. This is part of a CIHR team on stroke led by Helen Nickel. And again, the trainee Xiaoping Wei. This is just comparing what we can do at the synchrotron with what you can do clinically. As CT was mentioned as part of the PET-CT system, this is a GE64 slice machine that you would be imaged in the clinic. We're looking at a pretty small system here, but you can see the resolution, the detail we can get at the synchrotron is exquisite. This is something you really can't see with X-rays very well, and this is cartilage. Cartilage is almost invisible in a radiograph, and this is using a method called diffraction-enhanced imaging, CT, where we reconstruct soft tissues, and you can see there's some of the structure there you see is a ligament. The only thing that really shows up really well is the bone, but all this other stuff is soft tissue, including muscle, which is quite remarkable that we can see that with X-rays. This is in the area of developmental biology. One of the professors is interested in the earliest formation of teeth, how that process happens, and because of the very high resolution and access to unique contrast mechanisms, we can actually see those teeth. So this is in a mouse, a fetal mouse. So this guy is probably no more than about 5 or 6 millimeters tall, really small. And again, kind of showing the range of things that we can get at with the synchrotron. This is looking at lungs. One of the things that X-rays are good at are being absorbed in things. And you would think the lungs would probably have the least contrast of anything, because there's mainly just air. And so I'm going to flip through a series of images. This is using diffraction-enhanced imaging, again, looking at lung function. So this group is from the Western College of Veterinary Medicine, interested in lung function. And I just want you to see what kind of contrast we get. So we have a knob. I'm going to turn that knob. So this guy's alive. So we move the knob a little bit. Bang. This is what we call the top image. And first of all, the lungs have extraordinary contrast. In some sense, they have more contrast than you would ever get from bone, which is remarkable to begin with. But you can see his fur. So again, the detail and the kinds of things we can get at with the synchrotron are quite remarkable. Let me come back down the other side. So I want to begin to wrap up. First of all, I just want to mention that none of this stuff would not happen without people. And so on the beamline itself, we have our lead beamline scientist, Tomasz Wysokinski. He's here. He's sitting in the front row. We also, I think we have Denise Miller here, who helps do our controls. Adam Webb, I believe, is here as well. George Belev is another one of our beamline scientists. So these are all the people that make this thing work. It's all about people. But I think what we have, certainly at the CLS, and these other things that have been talked about today, I think we have a very unique opportunity for biomedical research. We are in a perfect environment to do that. And I think that part of the key of doing that is not just us doing things in terms of research, it's training the next generation of researchers. And I think that's a very critical piece, and certainly being part of a university, that's the key to make sure that these things go forward and advance. Thank you.